Hello, in this video I will be presenting our work titled Counterfactual Explanation and Causal Inference in the Service of Robustness in Robot Control by Simon Smith and Subramanian Ramamoorthy. As an overview of our work, we present a training method for a generative model with an autoencoder architecture that receives data point as images as inputs, where the model generates a counterfactual from the original image to explain classification and regression in a robotic control setting. Also, we use the generative model as a novel tool for robustness analysis in a model predictive robotic control task. To introduce the notion of counterfactual, imagine an example. If kangaroos had no tails, they would topple over. Here we have a notion of original configuration where we can assume as known knowledge that kangaroos have tails, a modification to the original configuration in conditional terms, if kangaroos had no tails, and as a result that is causally related to said modification or intervention. Also, we can understand counterfactuals as the modification of event A to cause B instead of C. Counterfactuals are related to one instance, data point, or event, not to a distribution of events. They are not necessarily present in the original data, and they can be imagined or hallucinated. For them to be useful as explanation, for example, of a classification, they should be the smallest modification to the original instance. Also, this modification should be realistic in the sense that they are close to the original data distribution. In the most simple classification setting, which means finding an counterfactual to explain a classification, we can write the search of a counterfactual as the x prime that minimizes a distance function between the original instance and the counterfactual one, and that it conveys the desired classification, in this case T sub C by a classifier C. Following an adversarial training method where the models are implemented as deep neural networks, we are able to train a generative model that for any input image x, it will generate the counterfactual x prime that satisfies the previously mentioned constraints. The constraints are imposed to the system as losses during the training of the generator. First, LG, that accounts for the difference between the original and generated data point, and second, LC, that accounts for the new instance to be classified as belonging to a target class. Here, the role of the classifier is to impose realistic modifications to the original data point, which means modifications introduced by the generator that fool the classifier into believing that the counterfactual is part of the target class distribution. First, we train the counterfactual generator on mNIST digits dataset. Here, the original class are number zeros and the target class is number 8. The top images are the original numbers and the bottom ones have been generated by the counterfactual generator after training. You can notice that the shape of the original data is maintained, while a line in the middle is the most common modification for classifying the original 0 as an 8. Then we tried with the celebrities data phase, where the original classes are faces without sunglasses and without the smile attribute. The target class are the sunglasses class and the smile class. You can see how the counterfactual modifies the surrounding of the eyes to explain the sunglasses category. Similar to the smile category, the modification is focused on the lips of the original images. We adapt the original cGen architecture for regression tasks. In this case, compared to the classification one in the top right of the screen, we include a predictor P that takes the generated counterfactual and outputs a real value number. Now the loss of the generator, cGen, included the new loss term LP. that measures the distance between the predicted regression value and the user-defined target. Note that now the classifier assumes a role more closely related to a discriminator in the GAN architecture, only deciding if the generated counterfactual is part of the training images or not. We test the cGen for regression in two continuous robotic tasks. First, the robot has to move its end effector to the target object, in this case the red cube, while jumping through the other objects. A safety constraint is added, as for the robot to move to the next object, the distance to the next one cannot be larger than a set distance d. Otherwise, it results in a failed control. In order to backpropagate through the controller, we train a deep neural network with supervised learning from several examples of the behavior. The regression is done on the final distance between the end effector and the target cube. With that model, then we train the counterfactual generator to obtain solutions for failed controllers, which means modifications to the scene that will result in a prediction of distance 0 between the end effector and the red cube. In this example, the distance between the blue cube and the red one is larger than the allowed threshold, result in a failed control. The generated counterfactual adds a green cube between the last two objects. The third picture shows the difference between the original and counterfactual. Note that the purple blob identifies the counterfactually added object, and then there is reconstruction noise around the rest of the objects. Here, more examples with the original failed control on top and the counterfactuals at the bottom. Note that the model is able to add more than one object to close the gap if needed. Also, we tried the cGen model on a navigation task of a Husky robot on an oil rig platform. Using learning for demonstration, we can train a neural network-based controller for model predictive control. In this case, we ask the cGen to find the counterfactual as modifications to the scene, where the robot would follow a straight line shown as the red dots, while the actual model predictive controller is driving the robot through the yellow dots. The top images show the original scenario and the bottom one the counterfactual, where barriers are open and marks and objects are removed to allow the NPC to predict a line closer to the target one. Finally, we introduce a counterfactual measure for robustness analysis. Different to a standard robustness measure as the capacity of a plant to reject noise, here we can measure the magnitude of the counterfactual in the state space, where we can assume that a smaller and realistic counterfactual is due to a controller that has better generalization. For example, if a controller has been trained in scenarios where a barrier can be open, this would yield a counterfactual with such solution, while another controller where the only training states are the occurrence or not of the barrier, then the solution would be a larger counterfactual. To test this idea, we train 3 controllers with demonstrations from different sets of obstacles. Controller A with all the obstacles, barriers and cone, Control B with only cones and no barriers, and Control C without obstacles. We trained the counterfactual generator for each controller and presented the same scenario to all of them. Here, in the horizontal lines, the red tint shows the size of the counterfactual modification. A darker red means a larger one. You can see how Control V has larger values when presented in scenarios with the green barrier in it. Controller C has larger value in most scenarios with either objects. As baseline, we measure the response of all the controllers to random noise. Shown similar values for all of them before the controller is lost. The bars presents the average loss for all the scenarios. Controller A is more robust in the counterfactual sense, as the counterfactual to solve the controller are on average smaller than for the other controller. Despite all the controllers having the similar robustness to noise, the controller trained with more configuration requires less modification to the state space to return to a working regime. We have presented the use of counterfactuals to explain classification tasks with a generative model. The model can be used to solve image-based robotic control problems. And finally, we present the counterfactual loss as a measure for control robustness. Thank you for your time.